is this little equation that I've written on the board, delightfully in blue. Now, we have learned that this equation is actually written in moles, right?
Yeah.
So I could say, take 1 mole of nitrogen, put it together with 3 moles of hydrogen, and you're going to get 2 moles of NH3. Is that fair?
Yeah.
And we've discovered that along with that equation usually came quantities or ingredients that were given to us in the problem. And then we had to use these mole ratios to move back and forth between things. You may have thought we were done with that sort of stuff, but unfortunately we are not. Thank you so much. So watch. Up to this point, even though this equation is written in moles, you have felt pretty comfortable if I gave you stuff in grams, because wasn't it your ability to convert from grams to moles and then use the equation? Are you with me? You may even remember when we were going way back to Avogadro's number and talking about the mole at the very, very beginning. Didn't we say a mole is equal to 6.022 times 10 to the 23rd particles, and those particles could be anything? Yeah, molecules, whatever. So if I gave you a certain number of molecules, couldn't you also figure out the number of moles? You may be getting a glimpse of what I'm going to do here. So in one case, I was giving you grams, and I asked you to convert to moles to be able to use this equation. I didn't ask you. You just had to do it. And in the other, I gave you like molecules, and you had to convert to moles to do this. Now I want to point out something to you that you may or may not be aware of. But see this PV equals N RT? You know what that N is?
Moles.
It's moles. So you're not going to like this, I don't think, very much. But even if you don't like it, I feel like the concept behind it is something that you can grasp. And here's the idea. Instead of giving you grams and asking you to use this equation, we call anytime we use an equation and we do math, we call it stoichiometry, right? We're going to do gas stoichiometry. And that's going to involve this. It's going to involve recognizing that we can rearrange this equation if we want to solve for moles. And that's the very moles that we can plug back into this equation if we needed to. Are you with me? Let me point out something that may be uber obvious, but perhaps we may overlook it. This ideal gas law is only used when we have gases. Now, where does this manifest itself? Well, in this particular problem, we're all good because isn't everything in here a gas? But there are other problems where our equation is not all gases. It might be liquid gas. Do you follow? Please say yes.
Yes.
It's pathetic begging that way, I know. This equation can only be used to work to solve for moles when you're dealing with a gas in an equation. Are you with me? Now let me show you something else that you may not like. Additionally, couldn't they give us like grams and grams of things over here and then ask us to figure out like the temperature of this if they gave you other variables, as long as you had the moles of that? And that I'm going to show you a problem and how this works, shall we? So here's a problem, and this is a basic stoichiometric problem. And what you need to bear in mind is simply this, that whole section we did with limiting reactant and excess reactant, and I know that some of you guys are going to be like, oh no, man, we're going back to that. I thought we'd finished with that. No, we're going back to that. But the thing you need to be aware of is that we now have one more way to get to moles and another place to go from moles. Because remember, when we're dealing with a regular problem and I give you grams, can't you go from grams to moles? Or moles to grams if they asked you for mass? Or if they gave you a problem, they gave you moles, couldn't you go to particles if you wanted to? Now with this equation, PV equals nRT, we have a way to A, solve for moles to be able to use it in an equation, but also if they give us moles, then aren't there only 3 other variables in the problem, 1, 2, and 3, that can be solved? So if they gave us moles, couldn't we then use these other variables to solve for whatever variable was missing? And I'll show you how this works. So the problem is going to be with this equation is going to be given 47, please write this down, it will really help, grams N2 and 21.3 grams H2 if the temperature in the container is 20.0 degrees Celsius. You may be wondering why I use 20.0 a lot. You know why I use it a lot? Because it's super easy to add 273.15 to it. Isn't that how we convert from Celsius to Kelvin or vice versa? So I typically do this a lot. Temperature in the container is 20.0 degrees Celsius, and the container is 500.0 milliliters. What is the pressure of NH3? I've tried as best I can to write somewhat neatly. I do understand that that is a very rolling scale compared to some of your guys' writing. So what are they ultimately asking for in this problem? The pressure of NH3, right? Now, I'm going to do this because it's going to help me to keep track of things. I'm going to put the variables that they're giving us underneath each one of these things that they match up with. Is that okay? So in this particular problem, they're asking, what is the pressure of ammonia or NH3? Ammonia. So isn't this a fair variable writing right there? Hey, I want to know what the pressure is of NH3. What else did they give me in the problem that could be applicable to NH3? Okay, the 21.3 grams, but that's applicable to this, right? Because isn't that this right here? So we're going to write 21.3 grams underneath this. That fair? I'm just going to gather like terms. What else did they give us? 47.0 grams of N2. So I'm going to put that right here. Incidentally, whenever you're given 2 reactants and you're trying to ask for some information about a product, mustn't you know which one is the limiting reactant in order to be able to solve for something about the product? Now, for those of you like, come on, man, you're asking to solve for pressure? What the heck? Well, I want to refer you to this equation right here. See this equation, PV equals nRT? If they're asking me to solve for the pressure of NH3, mustn't there be some way, or mustn't we be given the volume, the moles, and the temperature, and don't we always know the R? So if they're asking us in the problem to solve for the pressure of this, there must be either a given of all the other variables or some way to figure it out. Does that kind of make sense? So let's keep on writing the pieces of information they give us in the problem. They say what? If the temperature in the container is what? 20.0 degrees Celsius. All right, so I'm going to write over here because I want to figure out the pressure of this, right? I'm going to gather like terms that hopefully are going to match up with these right here. The temperature here is 20.0 degrees Celsius. And remember, I can never use Celsius in a problem, can I? So in order to use it, mustn't I convert that to Kelvin? I know that it's really, really, really early, but I'm super encouraging you, which is a step above regular encouraging, that you don't have a moment where you like count the dots on the ceiling, because this does not have to be hard. You started doing that, right? Yeah. Doesn't have to be hard. All it literally is one step past our basic Pivnert problems. It's a way that we're getting that information. So in this case here, my temperature plus 273.15, I'm pretty sure that gives me my temperature of 293.15. I'm not worried about rounding right now. What else did they give us? They gave us a volume of 500 milliliters. Now, you could be forgiven if you have 500 milliliters if you just immediately divide by 1,000, because aren't there 1,000 milliliters in a liter, and convert to liters.
No,
you can't, because tell me why again, Megan. We have an R. So the information we have is temperature, volume, right? And we also know what R is. I'm going to put it in here just because I want you to be aware of it. 0.08206 latmas per molic, right? And there's one more piece of information we need in order to solve for pressure. Would you agree? What is it? Isn't it N? We're trying to solve, I'm going to circle this. We're trying to solve for this, and we have all the variables we need except for moles of this. Are you with me? Now, I want you to note something here. Do you see how I only put the pressure, temperature, volume, R, and N underneath NH3? Why did I not do that under N2 or H2? They asked us to solve for this, right? They asked us to solve for this. Thank you. So, and in this problem right here, didn't they just give us grams of this right here? They didn't give us the temperature and the pressure. Now, they did in terms of, like, then they gave you the temperature in the container and the volume. So, right, we could get the temperature and the volume in here. But what would it help us? Because we don't need to solve for anything here. We only need to solve for pressure here. So watch and see if this makes sense. And if you can draw this like click, 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 click thing, then this is going to be really, really helpful. Would you agree that if I can somehow or another solve for N based on the information they give us in this problem, couldn't I then plug this N in with these other variables and solve for P in this equation? So let's backtrack and let's see where we're at. Do you see how I have 47.0 grams of N2 and 21.3 grams of H2? And if I wanted to, would you guys all agree that I could convert these both to moles by using the periodic table? And then couldn't I figure out by using the limiting reactant how many moles of this I would get? I mean, I also figure out grams, but in this case, we don't want to figure out grams because we want to figure out moles because that allows us to complete this equation. Any questions on what I'm doing so far? Yes, ma'am.
Converting the grams to moles in the equation and using that to solve for pressure.
For using that to solve for moles of this, which will then, along with these other variables, allow us to solve for pressure.
Okay.
In essence, this problem can be broken up into two parts. One is a limiting reactant problem, and one is a gas problem. Let's start with the limiting reactant problem here. So couldn't I go like this and go, all right, I have 47.0 grams of N2. And if I use the molar mass from the periodic table of N2, that'd be 28.0, I want to say 1, maybe? What is it? I'm sorry?
It's 0.14.
0.14, so 0.1 grams of N2 for every 1 mole of N2. And for my hydrogen, don't I have 21.3 grams of H2? And I know the molar mass for this is 2.016 grams of H2 for every 1 mole of H2. If you're wondering, like, where did I get these numbers from again, let me remind you that we did a whole bunch of stuff where we looked on the periodic table to determine what the molar masses were. Yeah? So help me out here. Those of you who are typically my helpers with calculators, can you tell me what the number is here for nitrogen? 1.68 moles of N2. And how about here? I'm going to guess way more, right? 10.56 moles of H2. Now, isn't this what we actually have mole-wise of both of these things? Now, remember, and this is again, we're kind of cycling back to the last test where we dealt with limiting reactant and excess reactant and whatnot. If we know the moles of both of our reactants, can't we do that Jedi trick to divide by their coefficients to determine what the limiting reactant actually is? You guys remember us doing this? So if I have 1.68 moles of N2, isn't the coefficient for this 1? So wouldn't that be like this divided by 1? And so this is my Jedi number. Let's just call it the Jedi number, even though we know that it's not a real thing. We're never going to use this number for anything. Wouldn't that give us 1.68 moles of N2? And here, wouldn't we be dividing this by 3? Well, it's going to be a little bit more than 3, but here's what we have to verify. Can someone help me with that? What number do you actually get? 3.5 exactly, or 3.5 something? 3.5. So we're going to call it 3.500 because there's 4 significant figures in this problem, right? 3.50.
I guess 3.52.
Okay, 3.52 moles of H2. Just by virtue of looking at these numbers, isn't this the smaller number right here? So wouldn't that make this my limiting reactant? Remember, the Jedi numbers are not what we actually going to use to solve problems. Won't only be the numbers that are part of our limiting reactant. Yes, ma'am. It is, and that's why I put the extra significant figure. I caught myself, and then I failed to say it out loud. There's only 3 significant figures here in the problem. Therefore, you should only have 3 significant figures here. Therefore, you should have only 3 significant figures here. So I kind of fell in the vein of thought, and this is true. I can, unless I'm actually asked to present an answer, I can keep as many significant figures as I want throughout the entire problem until I'm finally asked to go, what is A? And I have to write the answer, and that's when I have to worry with my significant figures. So watch. Are you all okay with this being the number of moles of N2 and that being my limiting reactant? So now watch. Don't we need the moles of NH3 if we want to plug all these variables in to solve for the pressure of NH3? So mustn't we do this little jaunt from here to here? Now, you can probably do this in your head, but since this is my limiting reactant, right? Wouldn't I start with that and go 1.68 moles of N2? And wouldn't the mole ratio between this be 1 to 2? 1 mole to 2 moles. So I'm going to go 1 mole of N2 on the bottom and 2 moles of NH3 on the top. So in essence, all I'm doing is I'm multiplying the number of moles of N2 by 2 because the equation says I need 2 moles of NH3 for every 1 mole of N2. Yes, sir.
Or on like a test, will you be given limited reactant?
Absolutely.
Okay.
You can't, in fact, all the problems we're doing right now, they are unsolvable unless you actually have an equation to work with. Indeed. So because I don't want to do math in my head, and because Abby's usually been pretty good about this, what is the number of moles of NH3 we have? It's going to be something like 3.36. So not 4 at all. 3.36 moles of NH3. Now, this is a big deal because that is going to go right here. Now, I am really confident. I'm really confident that if I gave you a problem on any of the worksheets and I said this, here's the temperature, here's the volume, here's the moles, solve for pressure, that you guys would just knock that out of the park. Why? Because isn't that essentially, given all the variables except for one, solve for one? So aren't we just going to plug all this back into our Pivnert problem? And also practically now. So if we take a look at this, would you acknowledge that we want to get pressure by itself? So wouldn't we divide both sides by volume? So we go P equals nRT all over V. And don't we have all of the variables here? And the N was gained from the information they gave us over here. Okay? So if I plug it in now, and I set it up, I'm going to take the N that we solved for based on the reactants reacting together to form a certain amount of moles of this, and that's going to be on the top, 3.36 moles. And next to it, I'm going to have the ungodly 0.08206 latmas per molix, which again, terrible unit. And our temperature is going to be 293. I know I'm running into this stuff here, but since we don't need it anymore, I'm just going to erase it. Seems a shame to erase such brilliant prose. 293.15 on the top, and that's going to be Kelvin. And then on the bottom, I'm going to have 0.500 liters. And will you agree with me that that will be equal to my pressure? I beg your pardon?
Why is 0.500?
Not pressure, it's my volume.
Your volume. Why is
No, the whole problem is.
Oh, it's 500 milliliter. I thought that said mH. I was really confused.
Yeah, we don't often use the unit mH, but I can see how that would be confusing.
I thought it was like speed, miles per hour.
Okay. I don't really have too much of a response for that, but do you see where we're at right now?
Yes.
Wonderful. How are you enjoying that gum, though? Is that a thing?
No.
Let's put it right underneath Cody's name. I haven't decided my mood yet. It's not a great mood, so I feel like it's not going to go well for you, but we'll see. I mean, I did say a prayer at the beginning of class, right? So maybe I'll feel better. I don't know. So in this case right here, let's just get to canceling units. I'm going to go mole. I'm going to go KK, and I'm going to go LL. And if I'm not mistaken, wouldn't that leave us with ATM? Now, yeah, it's funny because just in case chemistry wasn't confusing enough for us, they love to use units that very closely resemble other units. Like you said, atoms. Yeah, atom, ATOM, atmosphere, ATM. Sweet. Thanks for doing that for us. Yes? Because Atmos is more letters. Listen, I'm not the boss of chemistry. I barely am the boss of my own classroom in my life, so I have no say in this. So if I do this math here, and again, wouldn't that just be this times this divided by this? What do I get? Does anyone have after the
161.650.
Say it one more time.
161.656.
0.656 ATM. That feels a little bit high.
Yeah, I solved it like twice.
Oh, because you're also dividing by 0.5. That makes sense. All right, so
It'll be 162.
and by the way, since we're dividing by, we're multiplying and we're doing significant figures with 3 significant figures, mustn't this become 162? Atmospheres. Now, I don't want to, so this is the actual answer. I'll make it a circle squiggle because that's fun.
Beautiful.
Thank you. Not often that anything I've done on the board has ever been referred to as beautiful, so I'm grateful. This is one of the downsides when you do problems on the fly. Do you know how much 162 atmospheres of pressure is?
It's a lot.
Well, what we feel here on the surface is 1 atmosphere. So and of the other choices you have, the surface is the best, man. 162 atmospheres is 162 times the pressure we feel. So this is a bad day happening. In fact, I would wager to say that whoever is doing this experiment, the conditions are intolerable or unconducive to living.
Is that like the Earth's core kind of pressure?
I don't know exactly, although I'd love to say that. I would say this, it's at hull crushing submarine pressures in the depths of like the what's that trench called? The Mariana, whatever trench. Marinara, sure. The Marinara Trench, as we know. Only lesser well known than the ranch. I give up. Hold on. Go.
Okay, so for pressure, so I understand what it is, but like, let's say you're on another planet, like the pressure wise, like I don't know. Is there like a lot of pressure on Mars, or is there less?
So you realize that right now, above the oceans, because when we're in the water, would you agree that water is creating pressure on us? And we did that. We watched the video, the Mythbusters, where it seriously showed that in 6 feet of water, you have almost crushing water in terms of like your ability to open and close a door, right? But if you go above the surface, all the pressure we feel is due to the gas particles hitting into us. And the reason that the gas particles hitting into us is because we have this thing called gravity. And gravity essentially pulls everything, including gas particles, down towards us, which is why when you go up 10,000 feet or higher, I guess it wouldn't be going down. When you go up 10,000 feet, now all of a sudden, the pressure you're going to feel is going to be way, way less. In fact, if you ever skydived before? Ever skydived before? I'm sorry. If you ever skydived before, I think that the range around 10,000 feet is kind of where the max is that they want you diving from, because if you go any higher, there's not enough air particles, to live.
Oh, well, you have zero air
So,
It's Mariana.
Mariana's Trench. Yes, thank you.
It's Mariana.
But
It's an oceanic trench.
how close is that to Mariana anyway, right? So watch. Getting back to her question, you should listen to this because this is super interesting. He said, hoping that Google lost its. You know what? You're gonna just lost your Googling privileges. Oh, yeah. By the way, for those of you not unfamiliar with this, I slipped back into my musical training because I played piano for like 10 years and I played the trombone, which is not the sexiest of instruments ever. But you know what I did there to you? I caused you to. So you're welcome. Maybe you understand it. No, I not want no more.
1,000 times the standard atmospheric pressure at sea level.
How much is it?
1,000
Okay, so that's way more. So this is like maybe a third of the way down that trench.
1,086.
So I've learned something new. So her question was, let's pretend we're recording this. Her question was, what if we went to Mars? What would that be like? Well, let me ask this question: Is the gravity on Mars the same as it is here? And in addition, are there the same number of gas particles on Mars as we have here? Like, do they have the same atmosphere that we do? So I don't know, and this would be a fun discovery, and I'm sure that in 3 seconds she's going to be like, Mars pressure atmosphere. But I would wager two things. One, that there's not as many gas particles, but I could be wrong. It could be replaced with like this terrible sulfur atmosphere, right? And then two, it depends on what the gravity is on Mars, because if the gravity is greater, then it's going to push all the gas particles down, and we'll feel more pressure. If the gravity is less, then the particles will be up higher, and we won't feel as much pressure. Now, you had a question about this problem?
Are we able to compare atmospheres to PSI or something?
Sure. Yeah. Well, tangible is what you learn, right? So we learned pounds because that was what was tangible to us, but in reality it should be kilograms. We learned miles per hour when it really should be kilometers per hour, right? There are other ones, but the 5 that we're using, the one you talk about, PSI, remember that English system and how fond we are of it?
Yeah.
That comes with its own risks because then the numbers don't match up very well, but yeah.
So we don't really use that.
We do in those weird cases where they're like, hello, if the pressure is such and such PSI, and then they give you the conversion. I spoke like a British person there. They gave you that number of PSI, then they could then ask you to convert that to a unit that we can use and then do it the rest of the way. So that'd be legit only if they gave you the conversion factor. Yes.
So thinking back to the barrier, like what would happen if like someone was like swim down there?
Oh, you die. You would get collapsed in because remember, pressure always goes from high to low. So if your pressure on the outside is greater than your pressure on this side, it would collapse you. In fact, that's one of the problems when you have like these. I'm talking. And when you have these underwater vehicles that go down there, especially like the submarines, they have very, very thick. I don't know what material they use, walls, because if you ever created a pressure differential, A, it would crush it like a can, or B, even at the depths you're going, the pressure sometimes on the outside is so great that it can collapse like thick steel as if it's nothing. Now, one of the things that I didn't show you was the Meat Man demo, where it actually shows the olden days that people had these helmets. There were these cast iron helmets, and then they had a tube of air that kind of pressurized them, and they would go down several hundred feet and be able to work on stuff on the bottom of the ocean. And the myth was that if the pressure was cut off, then the pressure would be so great that the people would get crushed up into their helmets. And they actually did the demo, and they proved it to be true. The pressure is so great that it actually caused their Meat Man, it was like a human being that they made out of like bones or whatever, actually got shoved up into the helmet because the pressure differential was so great. Now, if you want, I feel like you go really awry just looking up Meat Man in Google. So please don't do that. But if you do want to see this, I encourage you, go to YouTube, go Mythbusters Meat Man Experiment. It is worth your time to watch this, because the first time you see it, you're like, oh, whoa. But now we come back to the learning. So are you okay with this idea that all I've presented, like literally the only difference in what I've presented you today is this, that there's another way to solve for moles, Pivnert, and if we know moles, that's the gateway into a Pivnert problem. Now, obviously, unless we practice this, it's not going to become very familiar to you, and that's what we're going to do in just a minute. Before we do that, we're going to do we're going to kind of do a middle, words are hard for me sometimes, so we're just going to do a slight breaking point, and we're going to slide over to the gas laws. The gas laws. So they're in your notes. They're already in your notes, and the three gas laws we're going to learn are Boyle's Law, Charles' Law, and Guy-Lussac's Law. But I'm going to show you a way that you can do these laws simply by understanding how equations work. And to that end, I'm going to use Pivnert as our guiding light, as we often do in chemistry and in gas laws. I'm going to erase all this in case, unless someone wants to, anything more with this. Okay, so I'm erasing this except for the blue writing because I don't want to rewrite that.
Should we start like a new section?
Well, you have it in your notes already in the packet I gave you. You have a notes section where it talks about Boyle's Law, Charles' Law, and Guy-Lussac's Law.
For extra notes, I mean, like.
You could, because this may help you. So let me give you some incentive here. Next class period, literally the quiz I'm going to give you is write for me the three gas laws with all their variables and what's held constant. That's going to be the thing. Now, that might be frightening to you right now because who's memorized the gas laws?
You.
Well, okay, that's a good point. I have. But it's only because I've done them a lot of times. If I hadn't, this is what I would do. I would understand the relationship between P, V, N, R, and T. Now, I will say this to you, my dear students. I did not know this trick until I was actually studying for my MCATs. And so, you know how sometimes they'll ask you, what's the relationship between these two variables? Maybe they do, maybe they don't. But at some point in your academic career, they're going to say, what is the relationship between these two variables? And they'll say, is it directly proportional, indirectly proportional? Is it inverse of the square? There's a whole bunch of things. And let me show you what I wish I had learned in high school. And here it is. So these are some statements of truth that will help your life immeasurably when it comes to understanding how equations work. And here's how this looks. See this equation right here? Anytime that you want to compare any two variables, mustn't you hold everything else constant? I gave the terrible example of a slapping circle. But the reality is, if I want to compare pressure and volume to each other, mustn't these three things be held constant? Now, R is no problem because isn't R constant anyway? But let's pretend we have pressure and volume. Wallace, stay with me, dude. If you have to stand up even, I would really encourage you to. Here's the rule. Whenever two things are multiplied by each other on the same side of the equation, they are inversely proportional. anytime you have two things that are multiplied by each other on the same side of an equation, they are inversely proportional. Now, here's where I wish the gravitas of what I'm sharing with you here, like how incredibly helpful this will be in your entire academic, mathematical, or science career will be if you understand this. Because then you'll be able to take a look at very, very long equations and complex equations. And when they ask you questions like, what's the relationship between these two variables? As long as you know where they're positioned, you're going to be able to know the relationship. So literally what I could say is this. What's the relationship between pressure and volume? And you would say pressure and volume are inversely proportional as long as everything else is held constant. True story? Now, scenario number 2. What if two things are on opposite sides of the equation, like pressure and moles? Now, R is a constant, so by definition, R can't change, right? So we're not going to compare something to R because if I change something, R is still going to stay the same. Does that kind of make sense? This only works for variables that have the ability to go up and down. And here's the rule when you have things that are on opposite sides of the equation. So let's compare, in this case, let's do pressure and temperature. Let's do those two. So pressure and temperature. Anytime something is on opposite sides of the equation, now, and by that I mean on the top, on the opposite side, the relationship is directly proportional. Now, I want to show you something here because directly proportional is when things are on opposite sides of the equation or if they're divided by each other. So watch this if you would. If I were to take this t and if I were to rearrange this equation, would this not be a legitimate thing to do? If I'm rearranging, I don't know why I leave both n and r there, but if I rearrange this equation, if the t was originally here, wouldn't it also be down here if I wanted to rearrange? So watch, either things are on opposite sides of the equation and they're directly proportional, or if they're on top of each other, they're directly proportional. So they're being divided by each other. Yeah. Now, outside of the, it's hard to quantify how incredibly helpful this will be in your academic career. Particularly if you take any maths, or if you take any physicses, or if you take anything that requires you to do a ratio ever, when you start dealing with longer and more complex equations, it doesn't matter all the other things that are there. If this is on top of this, this is directly proportional to this. If this is next to this, it is inversely proportional. And by the way, let me remind you of what those two things mean. It means this. If one thing goes up and the other thing goes up at the same rate, that is directly proportional. If one thing goes up and the other thing goes down at the same rate, or vice versa, one thing goes down, the other thing goes up at the same rate, but opposite, that's inversely proportional. Are you with me? Yes. Absolutely. Oh, mwah. So remember I was talking to you, remember we had you guys bouncing around in that little space there and we messed with the variables? And what I said was, you right now are actually learning the gas laws without actually knowing that you're learning them. And that's going to come into play right now. So there are 3 gas laws. And I'm going to write them out for you. And I'm going to show you by using this pivot. I'm going to, if you don't mind, I'm going to put the pivot again. I'm going to leave it up here so you guys can look at it. I'm going to write the 3 different gas laws because each of these gas laws was a guy's life work in which they just compared 2 of the variables. Remember, aren't the 4 main variables P, V, N, and T? Where they compared 2 of the variables to each other and held everything else constant. So let's start with Boyle's law. And one of the things that you should know in all of these laws is this. And you can you at the very least, can you guys find this in your notes, your overall notes, the packet? Because that'll make your life a lot easier. Can you share with everyone where it actually is? Yes, ma'am. Yes, sir.
The variance directly is the same as variance.
Absolutely. So I can't remember what it was. So I one of my close friends at my old school was the BC and AP calculus teacher. And I can't remember if I said indirectly proportional or inverse. I think it was indirectly proportional. And he got so upset. There is no indirectly proportional. There's only inversely proportional. So directly and inversely. Or maybe it was directly and indirectly. I can't remember which one it was. But one of those two is wrong. Clearly, I I had it lodged in my brain forever. But one of those two is not the greatest expression. But we're chemists here in this classroom for the time that we're here. So if you say inversely or indirectly proportional, in both cases, I'm going to be like, solid. Okay? Now, if we have, and would you agree with me this R is always constant, right? So if I want to compare two variables, like pressure and volume to each other, mustn't I hold the moles and the temperature constant? So what they decided with all three of these gas laws is that they would always hold the moles constant. Always, in all the gas laws. Now, they didn't say, let's hold the moles constant. Can someone read for me in the notes what they actually say?
When the temperature and the mass of the gas are constant.
Stop. Should I say when the mass is held constant? So, because moles were not an easy thing to work with, you do realize that moles and mass are kind of joined at the hip, right? So in all of our laws, instead of saying moles are held constant, which they are, we're going to say mass is held constant. Is that fair? So what we'll do is this. We're going to say mass is held constant. So mass is constant. And in Boyle's law, he decided to also hold temperature constant. Now, we're going to play a game that's not a game at all, nor is it even slightly fun. But if I tell you that my mass, aka moles, are held constant, and my temperature also held constant, and come on, R is held constant, aren't we comparing these two variables? What's the relationship between those two variables?
Inversal.
So this is the beauty of what I just shared with you, and about three-quarters of you jumped on this right now. Instead of having to memorize that pressure and volume are inversely proportional, you can look up at the Pivnert equation, and aren't pressure and volume next to each other? So couldn't I then make the statement for Boyle's law, the mass is constant, the temperature is constant, and pressure is inversely proportional to volume. Now, you can do one of two things. They always ask you for the equation. And so you know how we had the combined gas law, which is P1 B1 over N1 T1 equals P2 B2 over N2 T2. Remember that? Remember that good stuff? Okay. Would you agree with me that in this case here, they've held the moles and the temperature constant? Yeah. So the equation that works for that is this. So in my quiz that I'm going to give you next class period, I'm going to ask you guys to tell me what the relationships are, what's held constant, and also tell me what the equation is that would work those two together. And that's this. Now, in your notes, they also gave you PV equals K. Do you guys see that in your notes? And that always confused me at first because I'm like, why are they saying it's equal to K? Well, they're saying pressure times volume is equal to a constant because everything else is held constant. So either of those two equations you can write for me. I beg your pardon? Oh, the line here does not need to be there. I was just showing how we got to that equation from the combined gas law. So now watch. Let's do this. Let's do this together. There's three laws. Would you acknowledge that in each of the three laws, mass is held constant, aka moles, right? Mass, moles are held constant, which means therefore of the other three, pressure, volume, and temperature, they'll always hold a different one constant and compare the other two. So for Boyle's law, they held temperature constant. Let's take a look at Charles' law. Now, Charles' law is very, very similar in that two things are held constant. And the one thing that is true of all these, isn't it that mass or moles is held constant? So when you're getting ready to write your quiz or to take your quiz, and I ask you, give me the gas laws, just write them for me. In all cases, you're just going to go ahead and look at this and go, hey, my moles are held constant, but you're not going to say moles because that's not the original transcript of it. You're going to say mass. Is everyone okay to understand that mass is the gateway drug to moles and vice versa? Should not have said drug in a classroom. I do understand that. So when I then again say mass is constant. Now, for Charles' law, pressure is constant. So now watch. If mass and pressure held constant and R is held constant, what are we comparing? Volume and temperature. I want to run that by you again. So mass is always held constant. So when we're doing one of these, this is always held constant, right? R is always held constant, right? So then the question is, of these three variables, which one will we hold constant to compare the other two? In scenario number 1 with Boyle's law, we held temperature constant and we compared these two. In Charles' law, we're holding pressure constant. So watch, what are we now comparing? Volume and temperature. Where's volume and where is temperature? Opposite sides of the equation. What's the rule for the proportionality when they're on opposite sides of the equation? They are directly proportional. So literally you can then say this. Therefore, that's the therefore symbol. Volume is directly proportional to temperature. Now, it comes back to what Lily Catherine said. Do you realize that if I asked you this, you would not need this table to do it? Do you guys remember the how you guys acted out the molecules in here? So if you can just think back to that, like what's happening with pressure and volume when temperature is held constant? What happened? It should make sense. Now, is everyone still with me? We have to have a formula with this, right? So I always encourage you to go back to your ideal gas law formula, or sorry, your combined gas law. Is it P1V1 over N1T1 equals P2V2 over N2T2? True story? Yeah? So what's held constant in this case? Isn't it always going to be moles? It's always going to be moles. What else is held constant? Pressure. This is the equation that matches up with Charles' law. Are you with me? So really all you need is you need to know what pivnert is, and then you need to know where or what side each of the variables is at, and you can tell me the relationship between all of these things. Lastly, Guy-Lussac's law, which is actually spelled Gay-Lussac. Lussac. I think there's only one S. Lussac. And with Guy-Lussac,
There are
two S's. As always, isn't mass constant?
Yeah.
There's only one variable we haven't done right now. Isn't it going to be volume? Now, if I take a look at this now and I say, all right, volume is constant, moles are constant, R is constant. Are we comparing P and T? What's the relationship between P and T? Directly. Now pause. Let's say you didn't have this at your disposal, and I just said to you this. If I raise the temperature, what will happen to gas particles' pressure? What would you say? Wouldn't it go up? Like on your own, because you've done so much with gases, wouldn't that make sense to be the case? So if all else fails and your math part of your brain's all like, ah, and freaks out, go back to what is reasonable. Remember, we raise the temperature of something, the particles move more quickly, therefore they create more pressure. So in this case here, the relationship is going to be this. Pressure is what? Directly proportional to temperature. And again, I'm going to want you to write an equation. So go back to our P1V1 over N1T1 equals P2V2 over N2T2. And what's held constant in this case? Isn't it N? And what else? Volume? Let me see how we can get the equation from that. Now, let me pause and I'm going to give you a mnemonic help, because in reality, I'm hoping that if I've done my job right now, if you guys see pivnert, couldn't you tell me what the relationship is between any of the two variables based on where they're located? If they're on opposite sides, they're directly proportional. If they're divided by each other, they're directly proportional. If they're multiplied by each other, they're inversely proportional, right? So the only thing you need to be aware of is, how do I know what's held constant? In every single one of these gas laws, will you agree with me, and will you write down when you're doing your gas law problem that mass is held constant? Mass is always held constant. So then the question is, which one of the variables that each of these guys choose to work with? And here's how I do it. And it's so stupid. So with Boyle's law, here's what I think about it. Boiling, you don't need no more temperature. So Boyle's law, temperature is constant. Wow, indeed. Charles' law. Now, this is where I don't want to say that I've learned to adapt with the times, but I'll share with you the example I used to use when I started teaching, and I could almost be gold star worthy. Catherine, have it ready. If someone gets this, did anyone ever seen the show Charles in Charge? You haven't? Okay, so no gold star for anyone. Charles in Charge was a sitcom, I want to say in the early 90s, maybe 80s, which was obviously behind your time, but now I'm seeing people watch everything on Netflix, so perhaps you've seen it. And here's the premise, and it's hilarious. This family, they hire a male nanny. And the male nanny was Chachi from Happy Days, which again is an old show. And can you imagine? And the family had like 8 kids. So can you imagine all the interaction, the comedic gold from a male person being the nanny and taking care of children? And so my students, my very first year of teaching, they said, oh yeah, Charles in Charge. And Charles has so much pressure in his life, he doesn't need any more. And so that was what they used. Now, I realized that since no one raised their hands understanding Charles in Charge, not the best example. So I'm going to go even farther back, but also forward to Charlie Brown. Now, I don't know if you understand the very toxic relationship he has with Lucy and the football, but over the years, does anyone even know what I'm talking about here? Because maybe I need to readjust this. Over the years, she has bullied him mercilessly. And it comes in the form of, kick the ball, Charlie Brown, kick the ball. And he understands that if he does go to kick it, she'll move the ball at the last second and he'll do some physics-defying loop in the air and end up on his back. This has happened every single time. This has happened in the entirety of the cartoon over the course of half a century. I would argue that it may be more helpful to you to think of Charles' law as Charlie Brown. And that poor guy, he has so much pressure on his life due to that Lucy fiend making him kick a ball that Charles' law pressure is not needed. Yeah? Now, Guy Loose X1, that's a little more tricky to come up with one for. And as you might imagine, the fact that the word is gay in there gave my students a whole lot of ideas as to where they were going to go with it. The very first student that said something was one that said, well, Ellen DeGeneres is gay. Well, so you know this probably, but she also had a sitcom, which was one of the most popular sitcoms in the country. I think it was the #1 ranked sitcom back in the 80s or early 90s. And it was huge news for like 3 weeks in advance. And I think it was NBC. They were broadcasting it. Oh, maybe it was CBS. They were broadcasting it everywhere that they were going to have the first openly gay kiss on network TV. And so my student said, well, I don't want to see that, so I'll just turn off the volume. And I'm like, God bless her. I don't want to explain how eyes work, but turning down the volume itself, probably not as effective at stopping what you don't want to see. Although I do imagine that she was probably thinking about back in the old days, we had TVs you had to actually turn off. I know, crazy. And then another student jumped in and said, well, my hairdresser is gay, and he always tries to put volume in my hair. And also he wears really loud clothing. So I'm like, turn down the volume. So whatever you, again, I am desperate for better examples than what I've just shared with you. But however you want to look at it, in this last case, wouldn't you agree that Guy Lusek, and how about this? By process of elimination, isn't the only thing left for Guy Lusek to hold constant be volume? And so volume's held constant. What's the relationship going to be between pressure and temperature? It's going to be directly proportional. Are you with me? I would wager that right now, if you were to close your notebook and literally all you did was have Pivnert in front of you, which you should be able to write on a test. If all you had was just Pivnert in front of you, and I asked you, write for me the 3 gas laws. Let's do it. Let's do it practically right now. So do not look down. Just look at me. Okay. Okay. Don't look at the board either. Eye contact only. Okay. So I want you to tell me what's held constant. So I'm going to move over here. So you're all going to look over at me. so that you do not look at the board that has it on here ready. So I'm going to tell you the gas law, and you're going to tell me what's held constant and what the relationship is. Okay? If you want to, you can write pivot on your paper in front of you so you have it, but I do not want you to look on the board. And I want to do proof of concept because literally right now, in 2 minutes, I could give you this quiz and you could score 100%. Wait, sometimes I come up with good ideas. Huh. Okay, watch. Ready? So first things first. What is held constant for Charles' law? Pressure is held constant. Now, as an ancillary, what also is always held constant? Mass, right? So we're going to say mass and pressure are held constant. What is the relationship between the other two variables? Volume is directly proportional to T. Now, the only thing that might be slightly difficult is then writing the equation for it. But couldn't you write the combined gas law down and just eliminate pressure and moles and when you have it? R is never included. You're right. But R is not in our combined gas law anyway, so we don't have to worry about it. All right, ready? Boyle's law. What's held constant? Temperature and? Come on. What are the other two variables? Pressure and volume. What's their relationship? Indirectly proportional. Come on now. How about Guy-Lussac? Volume and mass. What are the two variables? What's their relationship? I feel like my work here is done. Because you should write that, and by the way, that's on top of just understanding the mechanism of gases like you suggested before. But next class period, I'm going to give you a gift of a quiz. And the gift of the quiz is going to be simply this. Write for me the 3 gas laws in their entirety. That's going to include what's held constant, what the relationship is between the variables that aren't held constant, and a formula that would relate those two to each other. True story? Okay, so that's what I'm going to stop with on film right now.
So we only